All right, in 4.4, we're going to start talking about the graphs of log functions. And what we'll do in 4.4 is really exploit some stuff that we learned in previous sections. So this section won't be that bad. I think since we already understand what the graphs of exponential functions look like, and we understand what the graphs of functions that are inverses of each other look like, I think we'll be able to come up with a graph of log functions fairly easily, make a couple observations, and then call this section good. Let's first consider this function f of x equals the log base 2 of x. And what I want to do is get some more information about the function. Specifically, I want to find the inverse of this function. So you remember back from 1.7 that the way we find the inverse of a function is a 4-step process. First step, you just change the f of x into a y. So I got y equals the log base 2 of x. What you now have is an equation that represents this original function, but what I want is an equation that represents the inverse function. So because inverse functions, informally speaking, just switch the inputs and outputs of a function, I can just switch the x's and the y's. That gives me x equals the log base 2 of y, and now I have an equation that represents the inverse function. It's not written in function notation. To get it in function notation, I have to solve this equation for y. But fortunately, that's easy enough to do. If I want to get this y all by itself, I can just exploit what I know about logarithmic equations and exponential equations, that x equals the log base 2 of y is equivalent to y equals 2 raised up to the x power. If I change y into f inverse of x, I've now solved for the inverse function of log base 2 of x. The point that I'm trying to make is that log base 2 of x and 2 to the x power are inverse functions of each other. We can generalize that a little bit. There's nothing special about the number 2 floating around. The log base b for any b of x and b raised up to the x power are inverses of each other. And since we already understand what the graph of b to the x power looks like, and we understand how to get the graph of an inverse function from the graph of a function, we can look at the graph of 2 to the x power, and from that come up with the graph of log base 2 of x. So maybe you recall 2 to the x power, this exponential function. The way we think about that is 1 times 2 to the x power. That 1 tells us the y-intercept. So the graph of 2 to the x power should go through this point right here that has a height of 1 on the y-axis. And then the value of b tells us what we multiply the height of this function by every time we take one step to the right. So the height is currently 1. If I multiply 1 by 2, I get a height of 2 here. So when the x value equals 1, the y value should be equal 2. If I take one more step to the right, I have to multiply that 2 by 2, and that gets me up to 4, because 2 times 2 is 4. One more time, if I take another step to the right, now I'm over here at 3. 4 times 2 is 8, so the height at 3 should be equal to 8. And I have this outline of the right-hand side of this graph. If I take steps to the left, I'm dividing the y values by 2, so 8 divided by 2 is this 4. 4 divided by 2 is this 2. 2 divided by 1 is this 1. If I take 1 and divide it by 2, I get a half. If I divide it by 2 again, I get a quarter. Divided by 2 again, I get an eighth. And we see the heights of this graph getting really, really close to the x-axis here. Oh, right, I remember that. Exponential functions always have these horizontal asymptotes. So as I go to the left on my graph here, my graph is going to get arbitrarily close to my x-axis. I got some good news. When we learned about the graph of exponential functions, there were really 4 different cases we were interested in. We needed to study the case where a was a positive number, so the y-intercept was positive, in which case the graph always had a positive height. And when a was negative, in which case the y-intercept is negative and the graph is always negative. Then we also had to study b. b we knew was always a positive number, but it could be between 0 and 1, in which case my graph gets closer and closer to the x-axis as if I go to the right. Or it could be a number that's greater than 1, in which case my graph gets further away from the x-axis as I go to the right, like it is in this case here. Since we're interested in the log base b of x, and we recognize that the inverse function of log base b of x is always 1 times b to the x power, we're really only concerned with the case that the y-intercept is 1. We don't have to worry about the case where the y-intercept is negative and the height of the graph is always negative down here. That's kind of nice. Another thing that maybe you remember when we were talking about logs is that when we're talking about logs, we can always assume that this base here is a number that's greater than 1. It's not that there's anything wrong with having a base like a half, for example, but anything you could do with the log base 1/2, you can also do with the log base 2. So typically we assume that b is greater than 1 when we're talking about the base of a log. When we're talking about the base of an exponent, we just assume that b is positive. When we're talking about the base of a log, we assume that b is greater than 1. Since the point of this section is to learn about the graph of log functions, we're only interested in the case where b is greater than 1. And because the b that is the base of the log ends up being the same b that is the base of the exponent when we calculate its inverse function, we're only going to be looking at the graph of exponential functions that have values of b greater than 1, in other words, that have this shape. What I'm trying to say is that we don't have to worry about all 4 of the different shapes that exponential functions have. We only need to worry about one of those four when a is positive, namely the number 1, and b is a number greater than 1 so that it gets away from the x-axis as we go to the right. This graph will be sufficient for us to figure out what the graph of log base 2 of x looks like. And there's two different ways you can do that. The quicker way is just to recognize that the graph of an inverse function is the exact same as the graph of a function, except it's reflected over this line, y equals x. So if you can just take this green curve and reflect it over this line and see what that looks like, that'll give you the graph of log base 2 of x. For some people, that's hard to do, so what might be easier is to switch inputs and outputs. First thing, y equals b to the x, there's an implied 1 here. The a in a times b to the x was equal to 1. And since a always tells you the y-intercept, if a equals 1, the y-intercept is always 1. In other words, the point 0, 1 is on the graph. Well, since this is the inverse of that, these graphs will always have an x-intercept of 1. All exponential functions have a one-sided horizontal asymptote. And in the case that b is greater than 1, that one-sided horizontal asymptote goes off to the left. Really what that's saying is when your x values get negative, your y values get arbitrarily close to 0. Well, let's see if I'm switching inputs and outputs, then what that would be saying is that when my y values get negative, my x values get arbitrarily close to 0. In other words, if these graphs always have horizontal asymptotes, these graphs are always going to have vertical asymptotes. And if these horizontal asymptotes are always to the left, these vertical asymptotes will always be going down. One other useful observation over here. Remember what b does. B is how much we multiply the height by every time we take one step to the right. So in the case that the y-intercept is 1, when we take one step to the right, we're taking that 1 and multiplying it by whatever the base is equal to. What I'm saying is in the case that the y-intercept is 1, these graphs will always go through the point 1, b. Well, if these graphs always go through 1, b, and this is the inverse of that graph, these graphs are always going to go through b, 1. That can be a really useful fact if I just give you the graph in blue and I ask you what is the base of this logarithmic graph. All you got to do is look for a y value of 1 and determine what x value that corresponds with. Oh, let's see, the y value of 1, that's the height right here. It looks like the height right here is at 2. I guess b is equal to 2. I guess I have the graph of log base 2 of x. The last fact that I want to add is a comparison. So I have to draw a new graph, make it a little bit bigger because it's hard to see in here. It's getting really small. But if I have these two different exponential graphs and they both go through this point, which I'm going to assume is at 1 here, they both have the same y-intercept, we can compare their values of b. Remember, larger values of b get away from the x-axis quicker as I go to the right than smaller values of b. The graph in red must have a larger value of b because it gets away from the x-axis quicker as I go to the right, and it gets closer to the x-axis quicker when I go to the left. It's a bit of a mouthful, but I can summarize that with this writing here. Well, you probably already see where this is going. What if I have larger versus smaller values of b, and I'm talking about the logarithmic graphs? They're both going to go through this point at 1, 0 because all these logarithmic graphs have an x-intercept at 1, just like all of these exponential graphs have a y-intercept at 1. But now it's not a matter of how quickly they get away from the x-axis, it's a matter of how quickly they get away from the y-axis. The graph in red, the one with the larger base, is going to get away from the y-axis quicker. I know that that's a little bit hard to see, but this one is further from this line than this one is. As I go up, and the one in red is going to get closer to the y-axis quicker as I go down. I can summarize all that with this statement in blue. If you can tell that these graphs are both the graph of logarithmic functions and these graphs are both the graphs of exponential functions, and in both cases the red one has the larger base, that's everything that I'm trying to get at from this last comparison. And I think that's all the information that we need about the graphs of logarithmic functions.